So today in this video we're going to talk about Kirchoff's law. So what is Kirchoff's law? It is variation of delta enthalpy H with temperature. So we have seen when our temperature is same. So what is the delta H reaction? Okay, like when we talk about like a non-standard condition, delta reaction H will be equals to delta reaction Cp molar into dt. We are assuming that the delta reaction of H. So enthalpy of the change of the reaction, whole reaction is also varies with temperature. So we take the differential over this of this term delta reaction H and we integrate this like this. Now if we see again like if we talk about the change in internal energy of the reaction, so that is also equals to delta R CVM into dt. So that is the integral of that reaction. So these are at non-standard state. So at non-standard state we get to know this formula when the delta reaction of H changing with temperature. So when we talk about at standard state, so in the standard state delta reaction H naught of D integral with the integral of delta R Cp m dt. So that is when the reaction is happening in standard state. If we look the LHS of the reaction, what is the delta reaction H naught? So the delta reaction H we have seen already, that is the stoichiometric coefficient of product, molar enthalpy of product minus reactant one, and also the formation in terms of formation product minus reactant delta H formation. And in case of standard state is also formation of product minus formation of reactant. So that's how we deal with what is our delta reaction H naught, D of change in enthalpy of reaction at standard state. Now when it comes to like what is the reaction delta R CPM, so delta R CPM not equals to again product coefficient, product stoichiometric coefficient into their CPM at standard condition summation minus negative of reactant CPM of reactant. Okay, here is stoichiometric coefficient of reactant CPM reactant. Like if we talk about this reaction, what is the delta R of CPM? The molar heat capacity at constant pressure equals to CPM of X in solid liquid state, that is reactant 1, okay, that is product 1. So here we are assuming the product and here it is a reactant. So that's how we do right. Now if we let's see that the CPM, if we say that the delta reaction of Cp molar is temperature independent, from the range T1 to T2, so the reaction we write delta HR2 delta reaction H0 H1 delta R CPM T2 minus T1. So where delta R H2 is the enthalpy of a reaction at temperature T1 and delta R H1 equals to enthalpy of a reaction at temperature T2. So that's how in case of when our reaction is there. Okay, in reaction we have written delta H, okay, reaction. Now when we change the temperature from T1 to T2, so that's how we do write the enthalpy change equation. In case of internal energy also we do write by the same. Now there is one more way by we can know how do we calculate when when a product is B and reactant is A, it is changing from A to B, and temperature is T1, and the further temperature we have increased to T2. So we have a two path by which the reaction could be go. Like we have changed the reaction from A to B, and considering the temperature to be same, and within the B we have increased the temperature, or we can say we have within A we have increased the temperature, and from A to B the temperature is T2. Now the reaction is delta H2. So we have seen what is delta H1 and what is delta H2. It is the reaction enthalpy at temperature T1 and reaction enthalpy at temperature T2. So by both the cases the calculation should be same. So if we see go by this path, so A to B is delta H1 plus within the B when we increase the temperature at constant pressure. When we are enthalpy, we are talking about constant pressure. So it is Cp of B, T2 minus T1. Okay, now if we go by this process, we have kept the temperature of A from T1 to T2. So it is the reaction is delta H2. So from A when we have increased the temperature, it is simple Cpa T2 minus T1, and the enthalpy change is delta H2. If we put this delta H1 over here, so it is Cpb minus Cpa T2 minus T1. So this is delta Cp, that is delta H2 minus delta H1 equals to T2 minus T1. And we have already seen what do we mean by delta Cp. So delta Cp also we can calculate by Cp of products, that we have already seen, minus Cp of reactants. So now that we see, like if we see in example how if a reaction is given. So if we see the example like N2 plus 3H2 in gaseous state is forming 2NH3. So here delta Cp of the reaction, delta Cp will be given as 2 times Cp of ammonia on reactant is initially first, then Cp and N2 minus 3 times Cp of hydrogen gas. So that's how we do consider these all cases. So here we know delta. So if a Cp of function, see delta Cp is a function of temperature. If delta Cp is a function of temperature, so whenever we have seen, whenever delta Cp is the function of temperature, we cannot directly integrate delta T. So in that case a delta H2 minus delta H1 will be equals to integral of T1 to T2 delta Cp dt. So that's how we will calculate the delta H2 minus delta H1. So like if Cp, if the term is given like this is At, this is Bt square, this is Ct cube. So here we will be integrating by multiplying the dt over there, the definite integral that we know. But here the when it is the temperature independent, okay, when it is temperature independent, then we will integrate T2 minus T1, and delta Cp will be delta H2 minus delta H1 divided by T2 minus T1. So whatever the information we have, we could get from here. So whenever we have a term like delta H, okay, Cp, that is very mandatory that we assume that the from temperature range T1 to T2 Cp molar or whatever Cp is constant during the range. When it is not constant, then whenever we took its dt Cpm, so here we have to integrate by putting the value. We can't integrate directly dt. First we have to check whether it is Cpm is temperature dependent or not. So that's how we call it as a Kirchoff's law. That is the variation of delta reaction enthalpy with the temperature.